Standard autoregressive decoding is constrained by a strict mechanical limitation. It can only generate a single token per forward pass. Because of this sequential design, standard inference for large language models is entirely memory bandwidth bound. The processor spends the vast majority of its time waiting for data to load from memory, underutilizing the actual computational capacity of the GPU. The industry standard bypass for this limitation is speculative decoding. Mechanically, it deploys a lightweight draft model to predict a branching tree of upcoming tokens, allowing the massive base model to verify them all simultaneously in a single parallelized forward pass. In highly controlled testing environments processing a single request at a time, this successfully shifts the workload from memory bandwidth over to raw compute, delivering identifiable speedups. However, theoretical speedups measured in isolated tests often mask structural failures that trigger as soon as these systems are deployed at production scale. In live production environments, disaggregated inference engines must handle massive dynamic user traffic, requiring them to process requests in large batch sizes. This graph plots inference speedup against increasing batch sizes. While open-source implementations of speculative decoding show a 1.3 times speedup at a batch size of 2, the efficiency falls below the baseline, dropping to 0.7 times speedup as the batch size reaches 48. The cause of this collapse is a physical hardware threshold. At large batch sizes, the pipeline transitions out of being memory bandwidth bound and becomes entirely compute bound. In this compute-bound state, the mathematical overhead required to run the draft model actively consumes the exact hardware execution cycles that the base model needs to operate. The algorithm itself works, but the physical orchestration of the hardware cannot support it. To solve this, Meta's GenAI team overhauled their Eagle speculative decoding architecture. Eagle is Meta's specific architectural framework for managing draft and target models, explicitly redesigned for the Llama 3 and Llama 4 families. Their final benchmark achieved an inference latency of 4 milliseconds per token on a 400 billion parameter Llama 4 model. Securing this 1.4 to 2.0 times production speedup required Meta to co-optimize their algorithmic math with the physical realities of GPU execution cycles. A speculative decoding engine relies on its draft model's acceptance rate, measured as tokens per call, or TPC. TPC tracks the average number of drafted tokens successfully accepted by the base model in a single verification step. To maximize this metric, Meta deployed an online distillation protocol. This forces the draft model to mimic the base model by shifting input tokens right by one position into the embedding layer. The distillation utilizes a dual loss function, minimizing the L1 loss of the hidden states and the cross-entropy loss of generated logics. Meta then tested different internal architectures for the draft model, specifically pitting dense feed-forward networks against mixture of experts, or MOE layers. MOE routes data to specialized subnetworks rather than activating the entire model for every calculation. The testing revealed that a simple 3-layer dense draft model achieved the exact same tokens per call as the more complex MOE draft model. This finding had an immediate hardware impact. The dense model requires 10 times fewer parameters, reducing the compute overhead that causes large batch execution to collapse. However, a lightweight, accurate draft model is ineffective if the system chokes while trying to evaluate the proposed tokens. This brings us to the verification stage, where the base model must evaluate the entire branching tree of tokens generated by the draft model. Processing these tokens requires flattening the draft tree into a single sequence for batch processing. This action breaks standard causal attention masks, which rely on data being in a strict chronological order. Calculating a custom tree mask for the entire sequence scales poorly. The computational weight multiplies against query and context lengths, creating a significant latency spike. Meta bypassed this by splitting the attention computation into 2 distinct passes. The prefix pass computes standard, mask-free attention strictly between the query and historical context. The suffix pass applies the complex tree mask only to queries within the drafted tree itself. These 2 disjointed computations are then re-aggregated using a specific merge attentions operation, outputting the final attention score with 0 performance overhead. By mathematically circumventing the masking bottleneck, Meta eliminated the algorithmic slowdown, leaving only the physical hardware latency to resolve. To solve this, Meta shifted focus from the algorithms down to the bare metal hardware orchestration required in a disaggregated inference setup. This Gantt chart shows the hardware traces Meta used to monitor activity. The top lane tracks CPU execution, and the bottom tracks the GPU. The red gap identifies where the GPU sat idle, waiting for CPU instructions. This idle time peaked during the bookkeeping phase of Eagle. During this phase, the key value cache and hidden states must be rewound based on which drafted tokens were accepted. The key value cache stores previous token calculations, so the model doesn't have to recompute them. In standard implementations, the GPU halts while the CPU handles this bookkeeping phase. At large batch sizes, this pause creates compounding latency. Meta initiated a restructuring protocol to remove these unnecessary CPU-GPU synchronization points from the decoding flow. They decoupled the post-processing operations, allowing the CPU to execute bookkeeping instructions while the GPU is already active on the next kernel. By hiding these CPU operations behind long-running GPU validation kernels, system efficiency increased significantly, accelerating the total throughput. This asynchronous restructuring pushed raw GPU utilization up to 94% during production traffic. High-speed inference relies on a synchronized overlap of algorithmic efficiency and bare metal resource management. Combining these optimizations produced the final operational results for the Llama 3 and Llama 4 architectures. To manage varying traffic sizes in real time, Meta used a tree dispatcher, a routing mechanism that selects pre-computed static tree structures based on the exact batch size of the incoming request. This bar chart compares standard decoding against Eagle speculative decoding. These optimizations maintain a 1.4 to 2.0 times speedup even at production scale, driving a 10 to 30% reduction in latency and achieving the 4 millisecond per token benchmark. The next development beyond Eagle is an experimental architecture known as speculative decoding, or SOARO. In this framework, while the base model is running a verification pass, the draft model preemptively predicts the outcome of that verification. If correct, this eliminates the drafting wait time. These methods of accelerating inference reduce cloud computing costs while simultaneously preparing neural network architecture for an impending hardware migration. The industry timeline for 2026 indicates a move away from centralized monolithic cloud data centers toward highly distributed, localized compute networks. This shift is driven by physical requirements in the real world. Autonomous manufacturing and real-time physical AI require split-second, closed-loop actions. The latency of transmitting data to the cloud and back is unacceptable for these use cases. This constraint necessitates the deployment of agentic AI and small language models directly onto edge devices. Agentic AI refers to systems that can make autonomous, goal-directed decisions, while small language models, or SLMs, are compact, task-specific neural networks designed to run locally without continuous cloud connectivity. Edge environments possess a fraction of the power and compute capacity of a data center. Running standard autoregressive decoding on this constrained hardware is too slow to support complex reasoning. The architecture defined by Meta's Eagle addresses this. High algorithmic efficiency, dense draft models, and maximized GPU utilization. Engineering focus is moving away from simply scaling parameters toward localized, surgical inference optimization. Achieving this ultra-low latency inference provides the foundational engineering required to bridge the gap between digital intelligence and autonomous physical reality.